So in the previous module, we talked about the specifics of raster data, when you might want to use it, and some of the idiosyncrasies of the file formats. In this module, we're going to focus more on the vector data model. Now, the vector data model, as we've talked about in the first module, is made up of three different types of geometries: points, lines, and polygons, and then usually associated data tables with each one of the features, whether it be a point, a line, or a polygon, in the data set itself. So there are other more complicated types of geometries that are available, things like three-dimensional surfaces. But we're really just going to focus on the base three geometries: zero-dimensional points, one-dimensional lines, and two-dimensional areas. Now, it's important to know that the basic unit of all of these is a point and its coordinates. But the actual unit that you're going to deal with, if it's a polygon file, is the polygon. It's not the individual points of it. Now, again, raster data can be sort of the basis for vector data. As we see here, we can do some sort of outline of a vector data from raster data itself. And what this allows us to do is find a geometric or geographic entity and isolate it in some way. And from that, we can begin to do any sort of calculations of distance, of area, things like that might be very, very difficult to do if we simply tried to find those pixels in a raster image. But it is important to note that there is some schematization that happens here as well. We're never going to get the boundaries 100% perfect. Now, raster resolution, as we talked about in Module 2, is going to lead to a pixelization of the image as you zoom in and out. Raster data are not particularly flexible with regard to scale. However, vector data, conversely, are very flexible with regard to scale. So we can see here as we zoom in and out, further in on this image, with three vector data layers in here. We have states, we have highways, and we have cities. You can see that the individual points that are being sort of rendered here as little circles stay the same size. The width of the highways stays the same size, no matter how far zoomed in or out we are. The edges of the polygons of the states stay the same size as well. Now, regardless of whether we're dealing with points, lines, or polygons, they're all made up of points. So the points, a point shape file, or a point file, a point data layer, would be individual points, each with a record somewhere else. Lines are going to be a string of points, sort of with a start and an end. And polygons are going to be a string of points where the start and the end are the same. And the computer knows to render what is in the middle as somehow different from what's outside of that polygon. But they're all stored as XY coordinates within some particular coordinate system. Now we could have, say, points. An example would be the location of libraries, here which we see for South Bend, Indiana. Lines could be things like highways. It could be things like rivers. It could be things like a track through a forest. But each one of those lines is going to be made up of individual points. We might never see these under the hood in the files themselves, but there are a series of points that make up these polylines. And in fact, we call these individual points that make it up vertices. It's just the plural of the word vertex. It just means the points that make up that feature. We could also have polygons. In this case, we're seeing soil types. So this is something that's continuous across the area. But we could have polygons that weren't continuous, that had sort of areas that they didn't cover. If we had, say, the footprints of buildings or the location of a particular type of forest. And again, somewhere in the files themselves, we have a series of vertices that make up the points, that make up the polygon. Now, I already talked a little bit about the concept of schematization, but I want to just address this in a little bit more detail, because there's really very little in the real world that's perfectly precise. The different types of vector data are, in fact, choices that we're making to represent different geographic features. So something is always going to be lost. Boundaries are rarely ever a very distinct one thing or another. Imagine a forest. We could draw the boundary of a forest on a map, but if we zoomed in far enough, if we went there and looked at it, it's going to be some sort of gradation between whatever is on the outskirts and where the forest itself is. So there are not a lot of things that have perfect boundaries on them. So using a vector data model, we should always be aware of this schematization. It's not usually a problem just because of the detail that we want to use in our analysis. And using a vector model is going to allow us to do a much quicker type of analysis and render these things much, much more effectively. However, it is something that we should be aware of when we're working with raster or with vector data. Now, one thing that's very important in GIS, particularly in web GIS and in systems where we're rendering lots and lots of data all at the same time, is to be able to display things at different scales. And one of the advantages of the vector data model is this is easier to do with vector data. We can simply say, if you're zoomed out really far, don't display all of the points, or don't display things if you're zoomed in past a certain scale. Raster data, this is much more complicated. We'd have to create a different layer that was sort of the zoomed out version to be able to show all of those pixels. But really with vector data, it's much more easy to create these kind of dynamic zooming scales. So just to review some of the advantages and disadvantages of the vector data model. In contrast to raster data, vector data take up a lot less room on your hard drive. The file sizes tend to be a lot smaller. And that's simply because it's storing individual points and how they're related together, instead of every single pixel in that image. Because of their nature, because of there being points and being very distinct boundaries between things, they're very good for discrete features. Locations, boundaries, roads, things like that. They don't tend to do quite as well with things that grade from one thing into another, stuff like topography or density. Those are things that might be better represented with the raster data model. Vector data are much more flexible with regard to scale. It's easier to set rules for what happens when you zoom in and out on the map. It's easier to be able to zoom into a higher level of detail with them. And one of the big advantages that we'll talk about in just a moment here is that we can store a lot of different attributes associated with each feature. Whereas with raster data, often you'd have to have an entirely separate layer for a different data thing to be in the same layer. In the cases of vector data, it's very easy to just add another field to the table. Now, some of the disadvantages that we've already addressed a little bit, vector data tend to be a very schematized view of reality. There tend to be maybe artificial boundaries placed in there sometimes. And because of this, they tend to be less well suited for continuous phenomena. So let's turn to just talk a little bit about attribute data and about those tables that tend to be associated with vector data. Now, if we wanted to look at one of these tables, it should look remarkably like what you might think of as a data table in Excel or in some other spreadsheet program. We have our rows that are individual records, and we have our columns that are the fields. So every feature, whether it be a point, line, or polygon, has a record, and then it has a value for each one of those fields. That value might be blank, but it has to have something in there for each one of the records, for each one of the features that we have. Now, in contrast to a regular spreadsheet, it's better to think about these attribute tables as kind of a simple database. And the big difference between a spreadsheet and a database is usually that a database, for every field that we have one type of data that's going to go in there. So if we have a numeric field, we have to have numbers in there. Whereas in something like Excel or OpenOffice, a more conventional spreadsheet program, if I were to type in for an elevation field or something, I could type in values 3.6, 8.4, and then I could type high if I wanted to as well, or large. I can type words in a numeric field without any real repercussions for it. And that's prevented from happening in these attribute tables. But the attribute tables themselves are very important to GIS analysis. They're kind of a fundamental strength of the GIS system. And really can be more accurately viewed as part of a larger spatial database. So the structure of these is kind of crucial to the success of whatever analysis we're going to be working with. And we can tie these tables together either between each other based on spatial location or based on some sort of common or index field between them. We'll talk about this in a lot more detail in one of the other modules on tables and databases. So as far as physically storing vector data, it is a little bit different than we might think about from a more conventional way of thinking about how we store files on a computer. So we store vector data usually in what we call shape files. So each shape file is one layer, and that layer is either that shapefile is either a point shapefile, a polyline shapefile, or a polygon shapefile. And it's actually physically on the hard drive made up of several different files. So it's important to remember that we might have 3 to 6 different files all with the same name and with a different extension, so after the period. So we'd have one that would be the file name .shp, that's the main shapefile. We'd have one that's .shx, that's an index file. And then we'd actually have the attribute table is stored separately. from the rest on the hard drive. So it would be the name of the file .dbf. Now, we've talked a little bit about the strengths of vector data as far as being able to do selections, being able to do querying based on locations. And I want to just go into a little bit more detail on when we might want to do some of these different interactions with vector data. So we have two main ways that we can query vector data effectively in ArcGIS and in most GIS programs. One is by selecting by attributes, so by selecting by some part of the attribute table, and the other is selecting by location, so selecting geographically between different layers based on their proximity to each other. So just as an example of how we would do a select by attributes, and we'll do more of these in the demonstration for this module as well. But we might want to go through, in this case we have a shapefile representing all of the states of the US and their associated attribute table. So we might go through and select those features where the name is Arkansas. And you can see that the feature Arkansas has been selected here. We know this because of that cyan color. That sort of indicates that it's been selected, both in the data table and in the actual geography as well. But we're not limited to just doing one at a time. We could select all of those states that have a population of above 5 million. You can see all of those have been selected here. But we can also do select by locations. So we can go through and select individual things based on their proximity or based on spatial relationships between one layer and another. So here we have shapefiles representing US cities, lakes, and rivers, in addition to the actual states themselves. And if we just zoom in a little bit, we can do a selection where we might want to query what cities are within 10 kilometers of a lake. And we can do this using select by location. You can see that all of those particular cities have been selected here. We can also look at how things intersect. So we could say if we wanted to find out what polygons or polylines features intersect along their edges. Here we have my home state of South Carolina, and we can quite easily query what rivers intersect the boundaries of South Carolina. We can also look at distances, so we can query any features that are within a given distance from the edges of another one. We can do this by looking at what lakes are within 300 miles of Chicago, and here it pops up most of the Great Lakes. We can also look at what cities are within 10 miles of any river, so we can start with a polyline and query whatever points or anything else are within a proximity of that particular polyline. And we can do the same thing with polygons. So if we have these polygons representing the lakes, we can select all of the cities that are within 10 miles of any one of them. Now there are other more complicated ones. We can look at completely within relationships. So if I select Utah here, I can select afterwards, I can query what lakes are completely within the geography of the geometry of Utah. And you see the Great Salt Lake comes up here as being selected, but Lake Powell down in the south there does not, because there's a part of it that goes outside of the boundaries of Utah. Now there's some other kind of complex ones in here as well. We can do things like query what between different polygon layers where the center point of something is. So in this case, if I wanted to query what lakes have their center point within either South Carolina or Georgia, I can look at Clark's Hill Lake here. And if I do this for South Carolina, it's not selected. But if I do it for Georgia, it is. And that's because we're looking at the center point, the centroid of that polygon that represents Clark's Hill Lake. And what you notice is that in this case, the centroid, the center point of that polygon, is not actually within the polygon. So it's important to kind of keep in mind that some of these more complex spatial relationships might be a little bit more difficult to run the analysis on. So that's really the basics of the vector data model. And what we're going to do next is in the following module, we're going to talk a little bit about how we do projections, how we take three-dimensional data from both raster and data models and actually flatten them out and create a formal map out of them.